We will now discuss the different methods by which heat energy gets transferred from one place to another. What are the different methods of heat transfer? Thermal energy gets transferred from one place to another mainly by conduction, convection, and radiation. Let's take one at a time and talk about them. What is conduction? To conduct. Suppose I have a box of chocolate in the classroom and I want to distribute it to my students. I can take one chocolate and give it to the student next to me, and that student will pass it on to his next student, and like that it will get passed on from student to student until it reaches the very end of the class. And I can distribute the whole box of chocolate to the students in the class like that. In the same way, heat energy gets passed on from molecules and atoms in a conductor until it reaches the other end of the conductor. So conduction is a mode of heat transfer within an object due to the interaction between atoms and molecules without involving their bodily motion. In the classroom, nobody walks and picks a piece of chocolate. It's an interaction among the students, just get passed on from one to the other. Conduction in metals is specially assisted by motion of electrons which carry thermal energy from one place, one part of the conductor to the other. In fact, the theory of conduction involving the motion of electrons is a little more complicated, and we will not get into there in this course. As energy gets passed on from molecule to molecule or atom to atom, heat travels progressively from one end of the conductor to the other, and that's the reason why a spoon in a hot coffee, the end of the spoon gets hot. Is that right? Heat flows from the coffee to the spoon. All right, let's talk about conduction a little more detail. The figure shows a section of a conductor of length delta x. I have shown another section here. This is the length delta x. The temperature at one end is theta 1 and the temperature at the other end is theta 2. The area of cross-section of the conductor is A. Now, what is the drop in temperature between the ends of the conductor? This end is at a high temperature theta 1, the other end is at a low temperature theta 2, so that heat flows from the hot end to the cold end. Now, what is the drop in temperature? The drop in temperature is theta 1 minus theta 2. Now, this drop in temperature occurs along a length delta x. So we're now going to define an important term in conduction. That is the temperature gradient. What is the meaning of a gradient? That's a common thing that you come across in calculus, is that right? Gradient is the slope. What does the slope mean? It's the rate of change. What is the temperature gradient? The temperature gradient is the drop in temperature per unit length, the rate at which the temperature drops along the length of the conductor. So temperature gradient is a measure of the drop in temperature per unit length. In other words, it is theta 1 minus theta 2 divided by delta x. And we write it like this: delta theta divided by delta x. The change in temperature divided by the length. This is a measure of the drop in temperature. Of course, delta theta is theta 2 minus theta 1. Now tell me, what are the factors on which the rate of flow of heat along a conductor depend on? Now, heat will flow faster if the two ends of a conductor are at two different temperatures. Is that right? If the temperature difference is high, heat will flow at a faster rate. In the same way as if the height difference, the water will flow much faster if the height difference is very high. In the same way, if the temperature difference is very high, the heat will flow along a conductor much faster. Also, the amount of heat flow depends on the area across which the heat travels. So putting these together, we can make this statement. The rate of flow of heat in a conductor is directly proportional to the area of cross-section. Greater is the area of cross-section, greater will be the amount of heat that crosses it. So the rate of flow of heat is directly proportional to the area of cross-section A, and also it is directly proportional to the temperature gradient. Now, how will you write it as a mathematical equation? Can you write this as a mathematical equation? Yes. The rate of flow of heat, don't confuse between the two rates. The rate of flow of heat is the amount of heat that flows per unit time. And temperature gradient is the drop in temperature per unit length. The rate of flow of heat, you can actually call it the thermal current. What is the meaning of a current? You see, current is formed by anything that flows. When air flows, there is air current. When water flows, there is water current. Current is the rate of flow. The rate of flow of heat, called the thermal current, is directly proportional to the area of cross-section and the temperature gradient. Now that means I can replace the proportionality sign by using an equal sign, adding a constant. So delta Q by delta T, what did we say we call this quantity? The thermal current, equal to Ka delta theta by delta X. What did we say we call delta theta by delta X? The temperature gradient. Now, this constant K is called the thermal conductivity of the material. So, the rate of flow of heat equal to K, the constant, times the area of cross-section times the temperature gradient. K is the constant of proportionality and is called the thermal conductivity of the material. That means every conductor or every material has a value of K, the thermal conductivity. Now, K is measured in a unit called watt per meter per Kelvin. Now, how did this unit come? What is the unit of this quantity, delta Q divided by delta T? We call the thermal current. What is the unit of measuring heat? Heat is a form of energy. So delta Q is measured in joules. Delta Q by delta T is measured in joules per second. Joules per second is called watt, isn't it? So this is watt per meter. If you look at this, A has the unit of square meter. Delta X is measured in meter. So square meter divided by meter is a meter, and delta theta is Kelvin. So the unit of K is watt per meter per Kelvin. Now here I have given you some values of the thermal conductivities of some common materials. Aluminum has a thermal conductivity of 237 watt per meter per Kelvin, whereas air has a thermal conductivity of 0.026 watt per meter per Kelvin. So we say aluminum is a good conductor, or silver. Look at that, the value for silver, 429 watt per meter Kelvin. So silver is a very good conductor, whereas air is a very bad conductor. So we say air is a good insulator. See that? So you have good insulators and good conductors. The values of K will be useful as we move on to solve problems. Alright, so this is the equation we discussed earlier. The rate of flow of heat, the thermal current, equal to Ka delta theta by delta x. Delta Q by delta T is called the thermal current, and we will represent it by the letter I, the uppercase I. Now, the thermal current is measured in watt, joules per second. And so, we can now rewrite this equation, I equal to Ka delta theta by delta x. Okay. Now that means I can now write an equation for delta theta. What does delta theta stands for? The temperature difference. Now remember, it is the temperature difference that makes it possible for the heat to flow. The thermal current exists because of the temperature difference. So let's write an equation for that temperature difference. It is the temperature difference that makes the current possible. Delta theta equal to I times delta x divided by Ka. I hope you can understand these transformation of equations. Delta theta equal to I times delta x divided by Ka, and I wrote it like this, I times delta x divided by Ka. And I colored this delta x divided by Ka because it is a very important quantity. This quantity is called the thermal resistance of the material, and I represented that by R. So delta theta equal to I times R, where I is called the thermal current, that is delta Q by delta T, and R is called the thermal resistance, delta X divided by Ka. Alright, so that's our equation. R equal to delta X divided by Ka is called the thermal resistance of the material. And what is the unit for measuring R? R is measured in Kelvin per watt. Kelvin per watt. I want you to use the units of delta X, A and K and see how you get the unit of R as Kelvin per watt. Now look at this quantity. Delta X divided by K. This has a special significance. Delta X divided by K is called the R value of the material. Now, if you go to Home Depot to buy some insulating materials, now we use a lot of insulating materials when you build our homes, is that right? If you go to Home Depot to buy an insulating materials, it is rated for its R value. So notice that the R value is not the same as the thermal resistance. The thermal resistance is delta X divided by Ka, whereas the R value is simply delta X divided by K. In building industry, the insulating materials are classified using their R values in their ability to be a good insulator, in their ability to allow heat to pass through. That is the R value. Now, if two conductors of thermal resistances R1 and R2 are arranged in series. Now, how do we arrange two materials in series? Now, this is the arrangement of two materials in series. It means heat has to pass through one material and then through the other. So, combining materials in series will increase their thermal resistance. Is that right? Yes. So, thermal resistors are arranged in series like this. If the heat flows through the first, it then has to go through the second. That means the thermal resistance is increased. The total thermal resistance therefore is the sum of the two thermal resistors. This kind of an arrangement is called a series arrangement. A series arrangement. So if you want to have a very good thermal insulation, you arrange the insulators in series. Now, if you live in very cold climate, you know, windows are double glazed. In other words, there are two layers of glass and a layer of air in between. You know that air is a very good insulator. That means glass, air, glass, there are three materials in series. The heat has to pass through these three materials. You are increasing the thermal resistance so that it becomes a very good insulator. On the other hand, if they are arranged in parallel like this, that means heat can pass through either the first one or the second one. That means you are reducing the thermal resistance. A parallel arrangement will reduce the thermal resistance. If the total resistance is R, then 1 over R equal to 1 over R1 plus 1 over R2. We will see the same kind of arrangement of resistors in electricity. Well, we will look at that shortly, well, maybe a few weeks from now. Let's do a small problem. A copper bar 2 meters long has a circular cross-section of radius 1 centimeter. One end is kept at 100 degrees Celsius and the other end is kept at 0 degrees Celsius. The surface of the bar is insulated so that there is negligible heat loss through it. That means there is no heat loss through the surface. Heat passes through the material. Find 1, the thermal resistance of the bar. Well, if you know that formula, can you tell me what is the formula for thermal resistance? Isn't it delta X over Ka? Well, find the thermal resistance of the bar, find the thermal current, the temperature gradient, and the temperature of the bar 25 centimeter from the hot end. Alright, let's see what the given things are. We got a copper bar 2 meters long, delta X equal to 2 meters. We use delta X for the length. One end is at 100 degrees Celsius, the other end is at 0 degrees Celsius. What is the drop in temperature? Will be 100 minus 0. And the radius of the copper bar is like this, what I'm holding here. It is, can you see this? Well, I'm trying to see if I can put it about the light. But, well, the end is circular. The radius of this circular part is 1 centimeter, that is 0.01 meter. And what do you need the radius for? That will help us to find the area of cross-section. What is the area of cross-section if the area of cross-section is a circle? Well, that will be pi r squared, is that right? and this is a copper material, and K, the thermal conductivity for copper from our tables, is 401 watt per meter per Kelvin. The area of cross section of the bar is pi r squared, where r is 0.01 meter, and so that's equal to 3.14 times 10 to the negative 4 meter squared. So now you know the length of the copper rod, we know its area of cross section, we know the drop in temperature, we know the value of K, we practically know everything that we need. What is the thermal resistance R? This must be an uppercase R, not the lowercase r. The thermal resistance is R equal to delta X divided by Ka. We've got delta X, we've got K, and we've got A. Let's place those values there and calculate. Now you need to do all these calculations on your own. Always remember to keep a calculator, paper and pencil with you when you listen to the lecture. Alright, I got that value as 15.88 Kelvin per watt, and that is the thermal resistance. Well, we know the thermal resistance, we know the temperature difference delta theta. Can you use that to find the thermal current? What is the equation that we obtained for thermal current? Well, what is the equation we obtained for the temperature difference delta theta? Delta theta equal to I times R, where I is the thermal current and R is the thermal resistance. Delta theta equal to I times R. Therefore, I equal to delta theta divided by R. Delta theta is 100 minus 0, and R we just calculated. So the thermal current is 100 Kelvin divided by 15.88 Kelvin per watt, and that is 6.3 Kelvin per watt, and the thermal resistance is Kelvin per watt. Kelvin and Kelvin cancels, watt will go up, so you can see thermal current is 6.3 watt. What is our next part? The temperature gradient. What is the temperature gradient? Delta theta divided by delta X. And we know both those values. 100 Kelvin divided by 2 meter, that is 50 Kelvin per meter. What does that mean? As we go down from the hot end towards the cold end, the temperature will fall at the rate of 50 Kelvin per meter. So when it comes to 1 meter, the temperature will be 50 degrees Celsius. You see? There is a fall in temperature of 50 degrees per meter. We can use now that concept to find the next part. We want to find the temperature at 25 degrees from the hot end. What will be the temperature 25 degrees from the hot end? Knowing that the temperature gradient is 50 Kelvin per meter. Well, that will be 100 minus 50 Kelvin per meter multiplied by 0.25. Is that right? Because as you go down, the temperature will fall at the rate of 50 Kelvin per every meter. So the amount of fall will be the rate multiplied by the length. So 100 minus 50 Kelvin per meter times 0.25 meter. The temperature 25 centimeter from the hot end is 87.5 degrees Celsius. Okay, let's do another one. 2 metal cubes with 3 centimeter edges, one copper and the other aluminum, are arranged as shown in here. Now this is the copper and this is the aluminum. I think it is rather difficult for you to read when it is recorded because I used probably the wrong colors. Copper and aluminum are arranged so that the one end is at 100 degrees Celsius and the other end is at 0 degrees Celsius. What do we need to find? Find the thermal resistance of each cube. Well, the thermal resistance is delta X over Ka. So we need to know the delta X for each cube. Remember, each side is 0.03 meter. That means that is your delta X. And K for copper and K for aluminum we know. Right? Okay, let's put down the result. The area of cross-section for each cube. A cube means length and width and height are all the same. So what is the area of cross-section? Is 0.03 squared, which is 0.0009 meters squared. That is the area of each cube. And K for copper is 401 watt per meter Kelvin. And K for aluminum is 237 watt per meter Kelvin. Refer to the table that I gave you earlier. Now, we need to find the thermal resistance of each cube. Let's find the thermal resistance for copper. R copper is delta X divided by K copper times A. If you notice, for each cube, delta X is 0.03 meter and A is 0.0009 meter squared. Only change will be the value of K. So let's put all these values there. That will be 0.03 divided by 401 times 0.0009. And that will be 0.083 Kelvin per watt. That is the thermal resistance of copper. Similarly, let's find the thermal resistance of aluminum. Our aluminum is delta KL times A. The only difference is, this time, instead of 401 for K copper, we will use 237 for K aluminum. And that will be this number, that is 0.141 Kelvin per watt. So we found the thermal resistance of each cube. What is the thermal resistance of the two cube system? Well, how are they arranged? They are arranged in series. Therefore, the thermal resistance of the system is the sum of the two resistances. Alright, so R, the total resistance is resistance of copper plus the resistance of aluminum, and that will be 0.0831 plus 0.141, and that is 0.224. And that is the total thermal resistance. Well, can you now use this to find the thermal current? What is the equation that will help you to find the thermal current? Well, we know delta theta, the temperature difference, equal to I times R. You know the temperature difference, you know the thermal resistance, therefore we can find the thermal current. The thermal current is delta theta divided by R. Delta theta is 100 minus 0. R we just calculated, and therefore I equal to 446.4 watt. Now let me ask you, What does it mean that the thermal current is 446.4 watt? It means if you stand anywhere along the length of copper and aluminum and measure the heat flowing across that section per second, it will be 446.4 joules per second. Now, will the thermal current be different in copper and aluminum? When heat flows from copper to aluminum, will the flow of current be different? What do you think? Well, the flow of current cannot be different. The rate of flow has to be the same. That means the thermal current in copper and the thermal current in aluminum are the same, namely this 446.4 watt. That is very important in doing the next part of our problem. What is the next part that we need to find? We need to find the temperature at the interface. What is the temperature at that interface? Well, for that, I already talked about this. The thermal current in copper is the same as the thermal current in aluminum and is equal to the total thermal current I, which is 446.4 watt. So the thermal current we know, the resistance of copper we know. Is that right? We calculated the resistance of copper in the previous slide. So we know the thermal current in copper. We know the thermal resistance of copper. Can you find the temperature difference between the ends of copper? Yes, we can find the temperature difference delta theta. Our delta theta will be 100 minus theta, because 100 is the temperature on the left end of copper, and if theta is the temperature on the right end, the temperature difference between the ends of copper is 100 minus theta. And now, you know that I copper equal to delta theta divided by R copper, and therefore that delta theta will be, you can see 446.4 is 100 minus theta, delta theta, divided by 0.083. We can now solve for theta from there. 100 minus theta equal to 444 multiplied by 0.083. That is 37.1. And therefore theta equal to 62.9 degrees Celsius. That is the temperature at the interface. Okay, let's now talk about the second method of heat transfer. The second method of heat transfer is called convection. Convection. In fact, convection is so much common in nature. Most of the life on earth actually depends on convection currents. How do we get rains? Most of the time during the summer, the air near the earth gets very hot. And you know, hot air is less denser. It will rise. Hot air rises and cold air from above will come down. Now, the flow of air caused by this phenomenon is called a convection current. Now, you remember my chocolate example. I can ask each student to come here, take a chocolate and go back to the seat. So each student comes, takes a chocolate and goes back to the seat. You can see this is the phenomenon of convection. Convection is a method of heat transfer in which molecules in the warm region of a fluid rise and molecules from the cold region move in. This is because when heat is supplied to an object, it will expand, as we saw in the last part of this lesson. When an object expands, its density decreases. Is that right? A lower density means the object will become buoyant, just like a cork float in water. Air with low density will rise and cold air will sink to come and take its place, causing what is called a convection current. If you put a pot of water on the stove and if you watch it carefully, as the bottom gets hot, the water at the bottom becomes less denser, it will rise, and water from the top will go down. Now next time you put a pot of water on the stove, watch it. You can actually see that convection current. Water from the bottom rising and the water from the top falling, so that the water in the pot will get uniformly heated. So when air gets hot, it becomes less dense and it rises. Cold air will then move in, setting up a convection current. Now let me see if I can demonstrate a very limited convection current for you. Now this is an animation I took from a school science website. Now what this illustrates is you have a candle burning here. When the candle burns, the air immediately surrounding it will rise. And this is a very thin aluminum foil made in the form of a helix. Now what happens is, when hot air rises, that rising air will make that helix spin. You see, the spinning of the helix is an indication that there is air current, and that is convection current. All right, let's start it and take a look at it. There you are. You can actually see as the candle burns, the hot air rises, and the rising air makes the helix like aluminum spins. It's a very simple demonstration of convection current. I told you earlier that most of the weather patterns on the surface of the earth are actually caused by convection currents caused by the differential heating on the surface of the earth. Some part of the earth gets hotter faster than the other part. Now land and sea breeze are good examples of phenomenon caused by differentiated heating and the flow of air that follows. Now let me explain what a land and sea breeze is. You see, the specific heat of land is much smaller than the specific heat of water. That means during the day when the sun comes up, land will get very hot very fast, whereas the water will take a very long time to warm up. That means air above land will be warm, it will rise, and cold air from the sea will come in to take its place. You see that? Sea breeze. In the evening, the reverse process happens. The land will cool down faster, and the water will take a long time to cool down. The air above water is warm, it rises, and air from land will rush in to take its place. Land breeze. So all these phenomena are actually caused by the differentiated heating. Now look at how a room gets uniformly heated by placing a heater at one part of the room. The air immediately surrounding the heater gets very hot, it rises, and cold air will sink, and there will be a good circulation of air created in that room. Now, a mathematical description of convection is a very complex phenomenon. You know why? Because it depends on the temperature difference in different parts of the fluid. And the temperature difference is affected by the flow itself. Actually, the theory of chaos gives a good picture of the complexity of the process of convection. According to the theory of chaos, if a butterfly flutters its wings in Paris, that could create rain in New York. Well, it's a very complex phenomenon because it involves very intricate changes in many different forms. And so we are not going to discuss that. We're going to leave it at this. And let's now talk about the third method of heat transfer, that is the radiation. Radiation, what does that mean? Radiate. To radiate means to throw out. Now, the third method I can distribute my chocolate is I can take one chocolate and say, Thomas, catch. Is that right? I can pick another one and say, Rachel, catch. I can throw each piece of chocolate to my class. Radiation. Most all the energy that we receive from the sun is in the form of radiated energy. Sun simply throws its energy in the surrounding medium. Heat is a form of electromagnetic radiation. I want you to get an understanding of electromagnetic radiation. You see, when you heat an object, the object will give out radiation. It will throw away chunks of energy. This object at this temperature is giving out energy, chunks of energy called quantas of energy. I am radiating energy. We all radiate energy. And this radiated energy is a form of electromagnetic radiation. In fact, electromagnetic radiation comes in all different forms. Now, what are the different forms of electromagnetic radiation? Electromagnetic radiations are waves. They got wavelength and frequency. Now, the longest of the electromagnetic radiations are called radio waves. As the waves get shorter, you get microwaves, you get infrared. Infrared are heat rays. You get the visible light. You see, the light that makes us see things is a part of the electromagnetic radiation. And as the wavelengths get smaller and smaller and smaller, the energy of radiation increases. So you must have a fair understanding of electromagnetic radiation. Objects radiate energy in the form of electromagnetic waves at all temperatures, even at very low temperatures. The effects and properties of such radiation depends on the wavelength of the radiation. Right? Now, all these radiations, one characteristic of these electromagnetic radiations, all these radiations will travel in free space with the same speed. Now, what is the wave equation we discussed in Unit 1? Anybody recall the wave equation? V equal to F lambda. And for electromagnetic radiation, the speed is generally described using C. So we say C equal to F lambda. Now, for all radiation, C is a constant. C doesn't change. So if C doesn't change, when the wavelength increases, the frequency has to decrease. When the wavelength decreases, the frequency has to decrease. Now, heat waves are called infrared radiations, and they consist of larger waves than visible light. All right. Now, let me see if I can illustrate that by drawing waves for you. Now, the longest of all waves, if this is a very long wave, well, that could be a radio wave. Now, if the wave now becomes smaller It could be a microwave. Now it becomes smaller. There you have infrared. Infrared. And here you have visible light. Now, don't confuse here. When I draw these diagrams, don't think that all radio waves, you have only one type of radio waves. There are hundreds of thousands of different radio waves of long and short. We group them all together and call them radio waves. In the same way, visible light. Visible light consists of about 4,000 different waves. And you know, each wave is a color. So visible light actually contains about 4,000 different colors. I simply represent it by this wave, but it's a combination of 4,000 different waves. And as you go shorter and shorter, you get ultraviolet, X-rays, gamma rays, and so on. So electromagnetic radiations come in all different flavors of wavelength and frequency, but they all travel with the same speed. Now here I have a picture of the electromagnetic spectrum. There is the wavelength, look at that, wavelength in kilometers down to micrometer, 10 to the negative 6 meter, to nanometer, to picometer. You can see wavelength decreases. Now you can see here, what are the types of waves here? Radio waves, very long wave. Radio waves can be kilometers long. And you can see all these waves are classified radio waves, almost up to here. And now comes the microwaves. Wavelength about 10 to the negative 2 to about 10 to the negative 4. They are microwaves. Then these are the heat rays. You see, light alone does not carry heat. Heat rays are different radiations. So these are heat rays about 10 to the power of negative 4 to 10 to the power of negative 6 meter wavelength. They are very small waves. And look at the visible light. Visible light is only a very small part of the electromagnetic spectrum. And as the wavelength increases, you see that 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, and nanometer, you got X-rays. So, electromagnetic radiations come like radio waves, microwaves, heat radiations. Now, the radiations that we give out are mostly this infrared radiations. You see, if you want to build a night vision binocular, it actually uses infrared to detect people and things. And the light bulb, the visible light, is in that very small region. So when I put this light on, the light produced by this bulb is in this region. And you can see this light is made up of about 4,000 different colors. And as the wavelength decreases, you get ultraviolet. Now, when the wavelength is very small, the energy is very high. Ultraviolet radiations can actually penetrate your skin, and that's why you should not go and sit in the sun for a long time. Ultraviolet radiations can give you skin cancer. Is that right? Okay, let's move on and talk about radiations. Objects emit a wide spectrum of radiation at all temperatures, but a certain wavelength region will be prominent at a particular temperature. Now, you see, I told you that a human body will radiate infrared. Well, a human body will radiate also radio waves and other waves. But at a given temperature, one wavelength will be most prominent, although others will also be present. So the most prominent radiation emitted by an object depends on its temperature. Now, what is the sun's temperature? What is the surface temperature of the sun? It's about 5,000 degrees Celsius. If you heat this object to about 5,000 degrees Celsius, it will emit visible light. In fact, the most prominent radiation emitted at that temperature. Now look at this filament one more time. This filament is emitting now white light. What is the temperature of that filament? The most prominent radiation emitted by this filament is now white light. The temperature of the filament is in the region of 4,000 to 5,000 degrees Celsius. Now, I want you to watch this filament when the light goes off. As the filament cools down, the prominent radiation becomes red. You watch that carefully. The filament, look, did you see that? Well, it only lasts for a short while. When the bulb goes off, the filament turns red. That means as the temperature decreases, the most prominent radiation at that temperature is red, which has got a lower wavelength. Now, this picture illustrates that phenomenon. Now, as you increase the temperature, the bump on the graph represents the most prominent radiation. See, look at that. At 6,000 Kelvin, the most prominent radiation is the visible light. And the visible light is represented by these different colors. The most prominent radiation at about 4,000 Kelvin and about, yes, is about, that is the infrared, the heat radiations. So if I heat this object to about 2,000 or 3,000 degrees Celsius, it will turn red. It will emit infrared radiation. So the most prominent radiation emitted by an object depends on its temperature. All right. Okay. As the temperature increases, the wavelength of the most prominent radiation will decrease. You can see this is a plot of wavelength on the x-axis and the power of radiation in the y-axis. Now, as the temperature increases, you can see the most prominent radiation shift to the left. Is that right? Shift to the lower wavelength. As the temperature increases, the most prominent radiation will become shorter and shorter. Iron, for example, will glow red about 700 degrees Celsius. The most prominent wavelength at this temperature is infrared, which are heat rays. Well, in other words, the wavelength of the maximum intensity, you can see the y-axis is the intensity. Now, what is the wavelength that has the maximum intensity at a particular temperature? The wavelength of maximum intensity will shift to the left, will decrease as the temperature increases. Is that right? Now, this is a very important law in radiation. What is that law again? As the temperature increases, the wavelength of the maximum intensity radiation will decrease. It will become, the maximum intensity radiation will become shorter and shorter and shorter wavelength. A relation between wavelength of maximum intensity and the temperature of the radiating object is given by Wien's displacement law, a very important law, and I'm going to give that to you. This is what Wien's displacement law says. Lambda max, what does lambda max stands for? Wavelength of the maximum intensity radiation at a given temperature is 2.898 millimeter Kelvin divided by the temperature in Kelvin. The uppercase T means the temperature in Kelvin. This is Wien's displacement law. All objects emit and absorb radiation at all temperatures. The rate at which an object emits radiation is called the power radiated. I'm going to call it P sub R, and the amount of power radiated by an object is given by the law called Stephen-Boltzmann law. And Stephen-Boltzmann law is a relation between power radiated by an object, the area of the object, and the temperature of the object. Alright? The law simply says the amount of power radiated by an object of area A maintained at a temperature T, that is Kelvin temperature, is given by P sub R equal to E sigma A T to the power of 4. Obviously, these two quantities, E and sigma, are constants. Now, E is a constant called the emissivity of the material. Emissivity. And E has values for all materials ranging from 0 to 1. If an object is a perfect absorber and a perfect radiator, that object has an emissivity of 1. If there is an object which does not absorb any energy or does not radiate any energy, its value of E is 0. For a perfect radiator, E has value 1. And actually, a perfect radiator is called a black body. A black body absorbs all the radiations fall on it, and it emits maximum radiation at any temperature. A perfect radiator is sometimes referred to as a black body. So E is the emissivity of the material, and sigma is called Stephen's constant, which is determined experimentally, and it has this value, 5.6703 times 10 to the negative 8 watt per meter squared per Kelvin to the 4. Now, these values will be given to you in a problem, so you don't need to worry about it. So, the power radiated by an object of area A maintained at a temperature, absolute temperature or Kelvin temperature T, is P sub R equal to E sigma A T to the power 4. Now, this is a measure of the amount radiated by the object. At the same time, the object also absorbs energy. The amount of energy absorbed by an object depends on the temperature of the surrounding. You see, if I stand in a very warm room, I will be absorbing energy. If I stand in a very cold room, I will be radiating energy to the surroundings. So if T0 is the temperature of the surroundings, then the power absorbed by the object is given by PA equal to E sigma A T0 to the power of 4. So you can see power radiated depends on the temperature of the radiating object. The power absorbed depends on the temperature of the surroundings. Alright, therefore what is the net power radiated? You see, the net power radiated is the total power radiated minus the power absorbed. Is that right? So I can now write the net power radiated is this minus this, and that will be E sigma A times T to the power of 4 minus T0 to the power of 4. Okay, let's do a problem. Calculate lambda mass for a human black body. Well, what does human black body mean? Well, it simply means assume that human body is a perfect radiator. Assuming the surface temperature of our skin is 33 degrees Celsius. What is the equation for lambda max? Wien's displacement law. Lambda max is given by 2.898 millimeter Kelvin divided by the temperature in Kelvin. So in this case, the temperature has to be converted to Kelvin. That will be 2.898 millimeter Kelvin divided by 273 plus 30 is 306 Kelvin. That is 9.47 times 10 to the negative 6 meter. That is the wavelength of the maximum intensity radiation that is emitted by human body. And do you remember where does this radiation come in? It is in the infrared. So we emit infrared radiations, heat radiations all the time. Okay, let's do another one. The heating wires of a 1 kilowatt electric heater are red hot at a temperature of 900 degrees Celsius. Assuming that 100% of the heat output is due to radiation and that wires act as black body radiators, it means the value of E equal to 1. What is the effective area of the radiating surface? Well, we need to find A, the area of the surface. Let's pick our data. The power radiated P sub R is 1000 watt, 1 kilowatt. The temperature of the radiating object, that is the hot heater, is 273 plus 900, 1173 Kelvin. The temperature of the surroundings is 293 Kelvin. Sigma we know, the Stephen's constant, and E is given to be 1. It's a perfect radiator. What all we need to do is write down the equation for the net power radiated. The net power radiated is E sigma A T to the power of 4 minus T0 to the power of 4. And we know all these quantities except A. So solve for A. A will be equal to P net divided by E sigma times T to the power of 4 minus T0 to the power of 4. And now put in the values of all those numbers in there. Right? And that's equal to 9.4 times 10 to the negative 3 meters squared. That is the area of that heating wires. Okay. Well, we have now gone through briefly discussing the methods of heat transfer, and this brings us to the end of Unit 2, where we discussed, well, briefly thermodynamics. Now, once you come to the end of a unit, you must be getting ready for the exam at the end of the unit. So please go through that practice test and make sure you understand all the concept. All right? And then do test 2. And I will get back to you with next lesson in Unit 3 later. Okay?